हेलो, मेरी आवाज आ रही है?
यस सर।
अस्सलाम वालेकुम। ये हो नहीं रहा था एक्चुअली,
वालेकुम।
अब ये कनेक्ट हुआ, इसमें कुछ प्रॉब्लम थी। ओके, सबको मैंने कर दिया इन एडमिट। ओके, सो लेट अस स्टार्ट। मेरी आवाज बिल्कुल ठीक से आ रही है?
यस सर, यस सर।
ओके, तो ऐसा है कि मुझे जो तुम्हें इस साल पढ़ाना है वो है व्हाट वी कॉल, लेट मी शेयर स्क्रीन थोड़ा। ओके, हाँ, तो जो मुझे तुम्हें पढ़ाना है इस साल, वो जो कोर्स है हमारा, लेट मी एडमिट देम आल्सो, वो है अपना फंक्शनल एनालिसिस 1, फंक्शनल एनालिसिस। तो एक्चुअली ज्यादा डिफिकल्ट नहीं है, बेसिक कोर्स ही है अपना। देखिए, ओके, हाँ ठीक है। तो लेट मी राइट डाउन फर्स्ट, इट्स कॉल्ड, मतलब जो फंक्शनल एनालिसिस सेकंड भी है आगे, फोर्थ यूनिट में, पॉसिबली फोर्थ सेमेस्टर में, आई मीन टू से, जो फंक्शनल एनालिसिस हमारा है वन, it is a basic course of functional analysis, and of course it should involve analysis. तो इसका नाम फंक्शनल एनालिसिस क्यों है, पहले मैं इनको एडमिट करता हूँ। ओके, तो व्हाट आई वाज ट्राइंग टू से, वो शायद इस वक्त में तुम उसको अप्रिशिएट ना कर पाओ, बट आइडिया ये है जो तुमने अभी तक पढ़ा है ना, एब्स्ट्रैक्ट मैथमेटिक्स, यू नो, डूइंग मैथमेटिक्स विद एब्स्ट्रैक्ट स्ट्रक्चर्स। जैसे अगर मैं दो चीजें तुम्हें याद दिला दूं जो तुमने अब तक पढ़ी होगी, दो चीजें जो होगी, जैसे एल्जेब्रा, एब्स्ट्रैक्ट एल्जेब्रा में तुमने पढ़ा सी ग्रुप्स, राइट? वैसे एल्जेब्रा जिसे हम कहते हैं, एल्जेब्रा इन्वॉल्व्स द ऑपरेशंस ऑफ, जो ना बेसिक डेफिनेशन ऑफ एल्जेब्रा होगी, समथिंग दैट इन्वॉल्व्स ऑपरेशंस ऑफ एडिशन, ऑफ कोर्स मल्टीप्लिकेशन एंड डिवीजन एंड रूट एक्सट्रैक्शन। सो वो जो एल्जेब्राइक ऑपरेशंस कहते हैं मैंने, उसी में तुमने पढ़ा all those operations go in the sense of groups, where you apply those or define those operations for, rather than numbers, abstract objects. Abstract objects के लिए तुम algebraic operations define करते हो. By that I mean you take any set and define an operation, a binary operation on that, you know, which has got certain properties, closure and existence of identity and inverse and associativity and so on and so forth. Then you investigate that. Then you not only, you know, you think in terms of, you know, the objects get very abstract. Now you add two sets, you know, what you call cosets. You can define addition and multiplication on cosets, scalar multiplication. Not only groups, you also do it for an important class of objects, what we call vector spaces or linear spaces. So you do these algebraic operations on a set, the which you define. Okay, you have a set and you define an operation and that has certain properties, and then you talk about the functions and all that stuff between those two sets having that operation structure, you know, by that group structure or, you know, vector space structure. उसके बीच में functions की क्या-क्या properties हो सकती है, वो तुम देखते हो. इसी तरह से दूसरे साइड से तुम देखते हो व्हाट वी कॉल मैट्रिक स्पेसेस और टोपोलॉजी. और मैट्रिक स्पेसेस में क्या होता है, तुम यही काम करते हो, यू नो, यू टेक एन एब्स्ट्रैक्ट सेट एंड यू डिफाइन द नोशन ऑफ डिस्टेंस, you define the notion of length, the metric on an abstract set. उसी तरह से जिस तरह से तुम notion of a binary operation, something like addition multiplication, तुम define करते हो for an abstract group or abstract vector space, तुम उसी बिल्कुल वैसे ही तुम notion of length, what we call metric, define करते हो for some abstract set. You know, you have a set X, then you define a function from the Cartesian product of that set with itself to non-negative real numbers with certain properties, what you call a metric, like dxy is equal to dyx, no symmetry. So what happens in functional analysis? We bring both of these together. I mean to say, you take a set which already has an abstract algebraic structure, a vector space, a linear space. Then you define a notion of abstract length on that set. So let me sort of try to make it clearer and clearer as much as I can. In case you don't, you have to ask a question, raise your hand. I will give you a chance not to see what if there is a problem. So what I'm trying to say, for our basic objects of study in our course would be what we call normed linear spaces. Normed linear, we can also call them vector spaces. शॉर्ट में हम कभी कभी इसको NLSP कहेंगे, a normal linear space. What is it? It is a vector space or a linear space. वेक्टर स्पेस और ज्यादातर हम यूज करेंगे लीनियर स्पेस, मतलब एक ही है. मतलब by a vector space, what do you mean? You have a set X, right? And we define, there is another associated set which is a field, which could be a finite field, which could be a set of real numbers or set of complex numbers. But in our case, we will denote it by K. We will be talking about our field जो हमारा होगा, कहाँ गया इसका ये, हमारा जो फील्ड होगा उसको हम डिनोट करेंगे बाय K. अरे यार, उसको हम डिनोट करेंगे बाय दिस bold K, which in our case would be either the set of real numbers or the set of complex numbers. So what we are talking about, our basic object of study is a normal linear space, which is basically a vector space, vector slash linear space over the field of real numbers or the field of complex numbers. Now, what is a vector space? You already know that. So vector space is a set which has got two operations. One is what we call the internal operation. Under that operation, X is an abelian group. An abelian group means it has a group structure with respect to one operation, which we usually denote by a plus. Means that it is closed. If you take two things in X, X plus Y belongs to X, for all xy belonging to X, and of course then you also have X plus group operations. Y plus Z is always equal to X plus Y plus Z, right? Then you also have what we call additive identity, that X plus 0 is equal to 0 plus X, which is the same thing as X, where 0 is a member of X, which has this property. Then you have additive inverse, right? You got minus X plus X is equal to this additive identity, and of course then commutativity. अगर ये चार properties हैं with respect to an operation, Y plus X, so this is an additive abelian group. That's what we have now, what we call a vector space. Plus, we have got another operation, which is between the elements of this abstract set X, our vector space, and the underlying field, which in our situation it would be the set of real numbers or the set of complex numbers. So पहली property ये है कि alpha into X belongs to X for all alpha belonging to our field, which is capital K, and X belonging to X. Then we have these field operations, scalar multiplication properties, that alpha into X plus Y would always be equal to alpha into X plus alpha into Y. Should I continue with this, or क्योंकि तुम्हें पता है what's a linear space, है ना? इसी तरह से alpha plus beta into X would be equal to alpha X plus beta X, where alpha beta belong to our field, the underlying field of the vector space, and these X's and Y's belong to the set X, our vector space or linear space. So what I'm trying to say is, so we have a set X That is a linear space. Linear space means a vector space which has two operations, linear space over the set of real numbers or the set of complex numbers. And once we start, our starting object is a linear space, and we define on it a notion of length, what we call norm. Now, norm is a metric. ये वैसा ही है जैसा कोई मेट्रिक होता है, जैसे तुमने मेट्रिक स्पेसेस में पढ़ा होगा. तुमने पढ़ा है ना मेट्रिक स्पेसेस? टोपोलॉजी का कोर्स पढ़ा है ना? So norm हम define करते हैं over a linear space. It is a metric. It's a notion of length. Now the only different thing जो metric spaces में जब हम metric define करते थे, जो हमारा set है उसका कोई structure नहीं होता था. हमारा जो x होता था, it was just an arbitrary set. और arbitrary set में हम क्या करते थे? We defined कि उस पे एक function जिसकी ये property है कि dxy is equal to 0 if and only if x is equal to y. Of course, the xy is equal to dyx. And of course, the triangle inequality dxy is less than equal to dxz plus dzy. And this was true for all x, y, z in this all elements inside this set. Now here our set is already a linear space. It already has a structure. So when we define a metric, a norm is such a metric which respects the internal structure of x. Here there is no structure on x when we define a metric space. But when we define a norm, it is defined on a linear space, means that it has to take into consideration the internal algebraic structure of x. So norm, let me give you the definition of the norm. So norm, we usually denote it by this. This is the notion, the notation for the norm. It's a function from this vector space x to non-negative real numbers. You know, something like a metric. The only thing is, it has to involve, it has to take into consideration the algebraic structure. So इसकी जो properties है, such that, मतलब it's a function. So norm is a function like this from a vector space to the set of non-negative real numbers such that, पहली property, norm of x is equal to 0 if and only if x is equal to 0. यानी सिर्फ 0 वेक्टर का norm 0 हो सकता है. दूसरी property, norm of alpha into x is equal to modulus of alpha into norm of x. Now this is true for all x belonging to x, my vector space, and alpha belonging to the field K. Because x is a vector space, a linear space, so कोई भी vector space linear space है, so there is an associated field over K. So तीसरी property is x plus y का norm जो है, it's less than equal to norm of x plus norm of y. So अगर ये तीन properties हैं, तो we say this is a norm on x. Now this vector space, along with this structure, once we have defined this function on it, we call it a normed linear space. Now we have defined a norm on it. Normed linear space. A linear space along with this function. Now, as you can see, this notion of length, of course, length has to be non-negative. You know? So it takes its values in non-negative set of real numbers. Secondly, it connects this notion of length with the algebraic operations. This property, ये जो यहाँ पे है, it connects the notion of length, what is the length of alpha into x, scalar multiplication जो तुम कहते हो ना vector spaces में, उसका connection norm के साथ क्या होगा, और vector addition का connection norm के साथ क्या होगा, because we are involving here algebraic operations. The scalar multiplication and vector addition का जो हमने नया structure इस पे define किया, metric structure, उसका उसके algebraic operations के साथ क्या connection है, ये ordinary metric में नहीं होता है ना, क्योंकि वहां पे x need not be a vector space. So now a normal linear space is a linear space, a vector space over a field, set of real numbers or complex numbers, which has a norm defined on it. Now, best way to move forward is to think of now examples. So So of course we are generalizing our notion of length. Now as we know, jo R itself or C itself, they are vector spaces over themselves, are vector spaces. Now R is a vector space, of course, over R. C is a field, so it's a vector space over, I can think of it as a vector space over C, or I can also think of its vector space over R, because we can identify C as the vector space R2. But nevertheless, so if I take the set of real numbers, R is a vector space under ordinary addition. Under ordinary addition, because means it's an additive abelian group with respect to ordinary addition, means you add the way you add two numbers under addition, and scalar multiplication is just multiplication of numbers. So I can think of R as a vector space over itself, right? Then I can define my norm of X to be just modulus of X. So needless to say, all the properties are satisfied because mod of X is non-negative, and it would be zero if and modulus of a number is zero if and only if that number is zero. तो पहली प्रॉपर्टी हमारी कौन कौन सी प्रॉपर्टी थी नॉर्म की? एक तो ये थी कि norm of X is equal to zero if and only if X is zero, and if I take the scalar multiplication of that number, so it is equal to modulus of alpha into norm of X, and of course the triangle inequality. Let me write it down on the side. It is less than equal to norm of X plus norm of Y. So here also, if I take norm to be the modulus of the number, modulus of the real number, it defines all the properties. Because if we take alpha x, it would be just modulus of alpha x. Then I can write it as modulus of alpha into modulus of x, but modulus of x is the same as norm x, so pehli property, and of course the triangle inequality applies to real numbers also. So, okay, so this was a trivial example, you know, R. It's a vector space, it's also a normed space. So I can think of R along with its modulus that we know defined on R is a normed linear space. Okay, so I can just now let's move to more substantial examples. Now, so we just have to think about vector spaces. So let's जो तुम्हें encounter करते हो vector spaces say R3. Now this is what we call three-dimensional space. Now by this I mean X, it is set of all X's which is basically a triplet of real numbers. So I've got Xi belongs to R. So that's what I have. Now it's a vector space. It's a linear space over R. And the operations are what we call pointwise. So you've got X अगर बराबर है x1, x2, x3 के, and y बराबर है, let me call it y1, y2, y3, I can define my vector space operations by, as you know, x plus y, you just add the component wise, the vectors, x1 plus x2, sorry, x1 plus y1, x2 plus y2, x3 plus y3. And then you can define alpha into x to be just pointwise multiplication, alpha x1, alpha x2, alpha x3. So under these two operations, you already know it very well. This is a linear space. Now, if you define your norm to be norm of x to be the usual non-Euclidean distance, sorry. By that I mean I take it to be the square root of x1 square plus x2 square plus x3 square, then this indeed is a norm, means that it satisfies all the properties of the norm. Firstly, it is non-negative. I have taken the non-negative square root of these numbers. And of course, needless to say, if I had taken norm of alpha x under this definition, it would be square root of, it would be alpha x1 ka square plus alpha x2 ka square plus alpha x3 ka square, right? So that would be alpha is a real number, right? So then you could of course write it as alpha square into x1 square plus x2 square plus x3 square, which would be, of course, it would be modulus of alpha into square root of x1 square plus x2 square plus x3 square, and of course that is modulus of alpha into norm of x. तो पहली प्रॉपर्टी. सेकेंडली मतलब ये तो ऑब्वियस, ये एक प्रॉपर्टी. एंड ऑफ कोर्स मैं भूल ही गया था कि अगर x 0 है तो उसका मतलब ये हुआ कि दिस स्क्वायर रूट ऑफ x1 स्क्वायर प्लस x2 स्क्वायर प्लस x3 स्क्वायर ये 0 होगा, which can if and only be this is 0 if and only if x1 square plus x2 square plus x3 square is equal to 0. So you have sum of squares of real numbers is 0 if and only if each of them is 0, if and only if xi is equal to 0 for all I running from 1 to 3, which is the same thing as saying that x must be 0. And agar norm x 0 hai to x has to be the 0 vector. Then this is the second property, and the triangle inequality, which again is very easy. It is the special form of what we call Minkowski's inequality. You know Minkowski's inequality तुमने किया ना?
Yes, sir.
Yes, वो क्या है? So if you have got a number p which is greater than 1 but less than infinity, so that 1 by p plus 1 by q is equal to 1, then of course you have got Minkowski's inequality says you have got summation xi plus, actually मुझे लिखने की जरूरत नहीं थी 1 by p, ये तो मैंने extra लिख दिया. So if p is greater than 1, then you have क्या हो गया इसको, हाँ यहाँ पे है ये. Okay, so then you have this thing summation xi yi का whole raised power p whole raised power 1 by p is less than equal to summation xi raised power p whole raised power 1 by p plus summation yi whole raised power p whole raised power 1 by p. So this is Minkowski, yes, Minkowski inequality. And if you put p equal to 2, you get this thing summation modulus of xi plus yi. Of course, in our case, it would be I runs from 1 to 3, p equal 2 likh lo, right? Because 2 is greater than 1. This whole thing, यहाँ पे bracket है, 1 by 2 is less than equal to summation xi square whole raised power 1 by 2 plus summation yi square whole raised power 1 by 2. Of course, I runs from 1 to 3 because we are taking. So of course, this is nothing but norm of x plus y, because norm of x plus y is basically norm of x1 plus y1, x2 plus y2, x3 plus y3, which according to our definition of the norm that we have defined on R3, which is square root of x1 plus x2, sorry, x1 plus y1 ka whole square plus x2 plus y2 ka whole square plus x3 plus y3 ka whole square. And since it is square, there is no difference if I take the mod. Mod ka square, mod of x square is the same thing as x square. So I can write it as square root of, I can write it as summation mod of xi plus yi whole square. और चूंकि ऊपर square root है, it is nothing but summation xi plus yi whole square whole raised power 1 by 2, and apply this formula. So this would be less than equal to summation xi square whole raised power 1 by 2 plus summation yi square in mod whole raised power 1 by 2, which is the same thing as norm of x plus norm of y. Okay, so this is what I get. So it's a, so now I know that once I have got R3 along with a function which is nothing but the Euclidean distance norm of x, this summation xi square norm of x is equal to this whole raised power 1 by 2. वहां पर मैंने लिखा था ऐसे, तो डरने की जरूरत नहीं है, बात एक ही, ठीक है. तो अगर मैं इसको ऐसे डिफाइन करता हूं, ये जो स्ट्रक्चर हमें मिला, इट इज इंडीड अ नॉर्मल लीनियर स्पेस। यहां तक क्लियर है? किसी को कहीं पे कोई दिक्कत तो होनी चाहिए, सीखने में दिक्कत होती है तो ठीक है, ठीक है। कोई सुन रहा है? 31 लोग हैं, सभी सुन रहे हैं ना? ओके, कोई इशू नहीं। अगर किसी को है तो यू रेज योर हैंड, तो हम इसको आगे बढ़ाएंगे। सो ये तो सिंपल सी एग्जांपल थी एक नॉर्मल लीनियर स्पेस की। नाउ एज यू कुड सी, अगर मैं Rn कर देता, R3 को मैंने दिखाया था ना, R3 along with the norm जो हमने डिफाइन किया था, norm of x of this triplet of numbers is summation modulus of xi square I runs from 1 to 3 whole raised power 1 by 2. Now this is a normal linear space. This is a normal linear space. अगर मैं Rn लेता, मतलब all n tuples of real numbers जिसमें n components है, और अगर मैं norm को define करता ऐसे, norm of x is equal to summation modulus of xi whole square whole raised power 1 by 2 I runs from 1 to n. Again this अगर Rn then अगर ऐसे डिफाइन करेंगे, इट्स ऑब्वियस, हमें जो पिछले में किया था बिल्कुल वही स्टेप्स फॉलो करने थे। एग्जैक्टली इसी तरह से हम प्रूव कर सकते हैं कि देन Rn is a normed linear space. So in linear space, you already have a vector space operations. Then you define the notion of length like this. So you get a normal linear space. Simple examples. So I could also have thought about Cn, n tuples of complex numbers. Again, define the norm the same way. So Cn hota kya hai, set of complex numbers. When you take n complex numbers, x1, x2 up to xn, and of course xi are complex numbers. Right? Right. Okay. So then you define again the norm the same way. Summation I runs from 1 to n, xi square whole raised power 1 by 2, and apply the Minkowski inequality, everything all follows. So this is another example. So now we are dealing with certain examples of normal linear spaces. But this is the beginning. Since we want to do analysis, so there has got to be something to do with the infinity. So let me continue. Okay, we can, before moving ahead, I can also, how about this? Agar मैं लेता R3 and I define a norm on this. This time I define my norm of x to be maximum I runs from 1 to 3. यहाँ पे ध्यान देना तो modulus of xi. Does this definition, ये जो मैंने यहाँ define किया था, let me call it star, does this define a norm on R3? No, ये definition समझे? इसका मतलब ये है कि अगर मेरे पास वेक्टर है R3 में 1 2 3, इसका जो नॉर्म है वो है मैक्सिमम ऑफ द मॉडुलस ऑफ दीज, लेट मी डाउन। ओके, मान लो ये है, तो इसका नॉर्म है इस फॉर्मूला के हिसाब से, मैंने तीनों नंबर्स का लेना है, मतलब आई हैव टू टेक द मैक्सिमम ऑफ दिस सेट, मैक्सिमम ऑफ मॉड ऑफ 1, मॉड ऑफ -2, mod of -3. What is the maximum of this set? कोई बता सकता है? It is? इसका मैक्सिमम क्या होगा इस सेट का? So this is nothing but the set, इसका 3 होगा, है ना? यानी हम मान रहे हैं इसकी लेंथ 3 है ना, इस डेफिनेशन के हिसाब से, है ना? यूक्लिडियन डेफिनेशन के हिसाब से इसकी लेंथ क्या होगी? जो ना हमें पता है लेंथ का फॉर्मूला, जो हमने इससे पहले किया था, जब हमने दिखाया था वो नॉर्मल इनका स्क्वायर रूट ऑफ 1 स्क्वायर प्लस 2 स्क्वायर प्लस 3 स्क्वायर होगा स्क्वायर रूट ऑफ 9 10 दैट इज 14, है ना?
जी
है ना। लेकिन इस हिसाब से अगर मैं इसकी लेंथ देखूं तो 3 आएगी, इस हिसाब से होगा तो √14 है। द क्वेश्चन इज, क्या ये इज दिस अ वैलिड डेफिनेशन फॉर लेंथ, a वैलिड डेफिनेशन फॉर नॉर्म? कहने का मतलब, does this definition also satisfy this property that norm of x is 0 if and only if x is 0 vector, norm of alpha into x is equal to modulus of alpha into norm of x, और एंड क्या ये इन 3 प्रॉपर्टीज को सेटिस्फाई
करेगी।
करता है कि नहीं ये डेफिनेशन? अगर ये करता है सो इट इज अ वैलिड नॉर्म, although it is against our notion of length, जो हमारा यूजुअल नोशन ऑफ लेंथ है या जो यूक्लिडियन डेफिनेशन ऑफ लेंथ है उससे अलग है, लेकिन बट इट इज स्टिल अ वैलिड notion of length on R3. So let us check.
जी सर।
So let us check. इसके लिए मैं रब करता हूँ, ये अगर बीच में बंद हो जाए तो हम रिपीट करेंगे, हाँ, क्योंकि इसने मुझे वार्निंग दी कि टाइम कम हो रहा है, ठीक है ना। सो नेवरदलेस, ओके, तो जरा देखते हैं। पहली बात ऑब्वियस है कि ये जो नॉर्म ऑफ एक्स है ये नॉन नेगेटिव है, बिकॉज इट इज मैक्सिमम ऑफ नॉन नेगेटिव नंबर्स, एक्स आर रियल नंबर्स, है ना। यू हैव टू रिमेंबर
जी सर।
एक्स इज अ ट्रिपलेट ऑफ नंबर्स, एक्स इज अ ट्रिपलेट ऑफ नंबर्स। तो पहली प्रॉपर्टी डन, ठीक है ना। दूसरा, अगर नॉर्म ऑफ एक्स 0 है तो it means that maximum I greater than equal to 1 less than equal to 3 modulus of xi is equal to 0.
जीरो
है तो ये 0 होगा, है ना, क्योंकि इसकी डेफिनेशन ये है। Now you have got 3 non-negative real numbers, उनमें जो सबसे बड़ा है वो 0 है, तो उसका क्या मतलब हुआ? 0 नेगेटिव नहीं हो, मतलब सारे नंबर्स पॉजिटिव है, और मैं कह रहा हूं जो सबसे बड़ा है वो 0 है। ये तो तभी मुमकिन है इफ एंड
जब
ऑन,
सब जीरो होंगे।
जब सब 0 होंगे, और वो तभी मुमकिन है जब एक्स आई 0 होगा, क्योंकि किसी का मॉड, नंबर का मॉड तभी 0 होगा जब वो खुद 0 होगा, विच मीन्स दैट एक्स मस्ट बी अ 0 वेक्टर। तो दूसरी प्रॉपर्टी भी डन।
सेट।
अब देखनी है तीसरी और चौथी प्रॉपर्टी। एक्चुअली ये तो ऑब्वियस थी। सो लेट्स टेक दैट प्रॉपर्टी। सो लेट मी टेक अल्फा एक्स का नॉर्म। सो इट इज एक्चुअली लेंथ ऑफ, अगर मैं इसको लिखूं, इट इज अल्फा x1, अल्फा x2, alpha x3, right? Now that would be maximum of the set I runs from 1 to 3 mod of alpha xi, which is nothing but maximum 1 less than I less than equal to 3 modulus of alpha into xi is modulus of alpha into xi. अब I का इसके साथ अल्फा के साथ कोई कनेक्शन है ही नहीं, तो इसको मैं बाहर निकाल सकता हूँ। इट इज मॉडुलस ऑफ अल्फा into maximum I runs from 1 to 3 mod of xi, but that is nothing but mod of alpha into norm of x. Very good. तो एक और प्रॉपर्टी सेटिस्फाई हुई है ना,
जी सर।
modulus of alpha x is equal to mod of alpha into x, right? So this is called the principle. By the way, this property is actually scaling, how the notion of scaling a vector by a scale, हम उसको बड़ा छोटा कैसे करते हैं, उसी का एक है। How about the third property, the most important, triangle inequality? तो ट्रायंगल इनइक्वालिटी के लिए क्या होना चाहिए? You have got norm of x plus y, right? This is actually norm of x1 plus y1, comma, x2 plus y2, comma, x3 plus y3. And of course, by our definition of norm, so you have to take the maximum of the moduli of the components. So it would be I runs from 1 to 3 mod of xi plus yi, right? So that would be less than equal to, because each is less than equal to, because this is now the applying the triangle inequality for real numbers, because x and y are real numbers. So it would be maximum of I less than equal to 1 less than equal to 3 modulus of xi plus modulus of yi. यानी अगर मैं पहले मॉडुलस निकालूं, उनका सम करूं, और फिर सम के बाद उनका मैक्सिमम निकालता हूं, राइट? सम के बाद मैक्सिमम। दूसरा है देन इट वुड बी लेस देन और इक्वल टू, अगर मैं लूं मैक्सिमम पहले और सम बाद में करूं, I hope you can understand that. अगर नहीं तो थोड़ा सा सोचना. If you have a set of non-negative numbers, two sets of non-negative numbers, तो तुम क्या करते हो, पहले उनको पॉइंट वाइज ऐड करते हो ना, पहले को पहले के साथ, दूसरे को दूसरे के साथ, तीसरे को तीसरे के साथ, नॉन नेगेटिव नंबर्स, फिर उनका मैक्सिमम लेते हो. और दूसरा है, इसमें से सबसे बड़ा लेते हो, इसमें से सबसे बड़ा लेते हो, फिर तो जब तुम अगर तुम पहले मॉडुलस और फिर ऐड करोगे, पहले बड़ा लोगे फिर ऐड करोगे, तो वो बड़ा होगा उससे अगर तुम पहले ऐड करोगे और फिर बड़ा. मतलब you just can take some examples on your own, which is nothing but norm of x plus. तो तीसरी प्रॉपर्टी जो ट्रायंगल इनइक्वालिटी है, मोस्ट इंपॉर्टेंट प्रॉपर्टी, वो भी ये डेफिनेशन जो हम स्टार डेफिनेशन है, ये भी सेटिस्फाई करती है. सो इस तरह से अभी हमने देखा कि अब जो हमारा एब्स्ट्रैक्ट नोशन ऑफ लेंथ है फॉर ओवर नॉर्मल लीनियर स्पेस, सो इट कैन बी, इट जस्ट हैज टू, मतलब इट नीड नॉट बी आवर जनरल नोशन ऑफ यूक्लिडियन डिस्टेंस. सो इट कुड बी एनीथिंग व्हिच सेटिस्फाइज दीस थ्री प्रॉपर्टीज, राइट? ठीक है ना. नाउ आई कुड ऑल्सो हैव थॉट, अगर मैं इसको आर एन लेता, यही वाला आइडिया में यूज करके आई कुड हैव शोन दैट अगर मैं यहाँ पे एन लिखता और यहाँ पे भी एन लिखूं, फिर सो सारी प्रॉपर्टीज बिल्कुल एज इट इज फॉलो होंगी. मुझे यहाँ पे एन लिखना है और यहाँ पे भी एन लिखना है. सो दिस वुड बी अगेन अनदर नॉर्म अदर देन द यूक्लिडियन नॉर्म, यूक्लिडियन लेंथ on Rn. So then it would be, then Rn would be a normal linear space. So what I'm trying to say, given a linear space, given a vector space, you can have more than one, you can have many more than one notions of length, more than one norm defined on the same vector space, on the same vector space. अभी हमने दो देखे. I could have also done this. How about this? अगर मैं अभी लेता, चूंकि if I take this p is greater than 1, I define my norm of x to be summation modulus xi raised power p, I runs from 1 to n, whole raised power 1 by p. So ये कितने, these are infinitely many norms on Rn, और ये सारे के सारे norms होंगे, और on Cn. तो ये this is an infinite collection of norms for each p. हमने सिर्फ प्रूव किया था for p equal to 2, लेकिन मैं p equal to 3 भी ले सकता था, p equal to 2.5 भी ले सकता था, because जो triangle inequality है इसमें मेन चीज, it is set, it is valid for all p, which is the Minkowski inequality 1. So you can have more than one norm defined on the same vector space, same linear space. So before going any further, we can think of, now if I define my dx, now given, now you have got a normed linear space. Normal linear space means you have a vector space और उसपे मैंने norm define किया था. Now if I define d of xy to be norm of x minus y, because it's a normal space, it's a normal linear space, so subtract मैं कर सकता हूँ vectors को, तो यहाँ पे subtraction operation आ गया. तो ये जो dxy जब भी मैं ऐसे define करूँगा, it will satisfy, it is a metric. तो अगर मैं d of xy को ऐसे define करूँ with the help of the norm, so it is a metric. So that means every